Welcome back to .NET Rocks. This is Carl Franklin.
And I'm Richard Campbell.
And we're here at Sydney, NDC, Sydney to be exact.
Did the boat cruise last night. That was fun.
Oh man, that was awesome. Yeah, they went out, they took us out on a boat, which was really like a floating restaurant.
Yeah, it was
with glass walls.
It was a bit noisy, actually. All glass all the way around you. It was like a people aquarium, really.
They took us out by the Sydney Opera House and they just slowly twirled the boat around so we could just be there for a while, because it's not very far to go.
And the bridge, too.
Yeah, and the bridge.
It was awesome.
It was awesome. And this is going to be a great show because we're here with John Azariah, and we're going to be talking Q# in a little bit. But first, we have this little thing called Better Know a Framework. Roll the crazy music. So yeah, we don't actually play the music when we do a live show.
Yeah.
Unless you guys
we don't play music on any of the shows. We add it in later.
Unless you guys want to sing it.
Can you sing
1, 2, 3, go. Da, 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 da. All right. That's enough of that.
All that gets edited out.
Yep.
Ready?
Yeah.
All right, buddy. What do you got?
This is crazy, but this is an article in The Verge. Windows 95. Remember that?
Yeah,
it's
like
now
13 years ago.
Yeah, it's now an app that you can download and install on Mac OS, Windows, and Linux.
What?
It's written in Electron. I swear to God, I'm not making this up. The guy behind Slack, Felix Reisberg, did this.
Okay.
Yeah, so now you can run Windows 95 as an Electron app.
This is Electron run amok. That's what this is.
Yes, it's crazy.
This is not a good idea.
No, it's crazy, but look, there it is.
That's funny.
You can't see it, but just go there. This is actually show 1587, so if you go to 1587.pwop.me, that will link you right to it.
That's awesome, dude. I love it.
What else can you say? I mean,
you got it. It's just standing there. It's
every once in a while, you need a little Minesweeper.
Minesweeper.
Yeah.
I bet there's a somewhat smaller way to run Minesweeper. I'm just guessing, rather than emulating an entire operating system to play Minesweeper.
Probably.
Okay.
That's what I do with it.
I love it, though.
Yeah. Who's talking to us, my friend?
We haven't done a lot of shows around quantum computing, except we did do that Geek Out.
The Geek Out.
That was in 2015. Yeah. So this is a comment from show 1196, which was the Quantum Computing Geek Out. And I'm laughing at the abstract I wrote, again, 3 years ago now. Where I said, the state of quantum computing today, 3 years ago, is like the state of classical computing in the 1950s before the advent of the transistor. Because we're still feeling around for the fundamentals of what qubits should look like. There's competing strategies.
What's a qubit?
Nice.
Never mind, that's another show.
Yeah. And not as funny as it used to be either.
No, apparently.
Which too bad. This comment comes, and while that show was recorded 3 years ago, this is a comment that's only 9 months old. This is from Tom Atwood. He said, "Hi, Carl and Richard. I just saw Microsoft's release of Q# and its quantum development kit and thought, hey, Carl and Richard did a show on quantum computing just a few months back. I should re-listen. And then I went searching for the show, and it was 2.5 years ago. I guess time flies when we're having fun. Is there any chance that you could find someone who could do a show on Q# and the quantum development kit? Thanks so much for the great podcast."
Yeah.
No.
Yeah,
can't do it. Sorry, Tom. No. Can't do that.
We refuse to talk about Q#.
I find the whole thing really gauche, actually.
Yeah.
Really.
Yeah.
All right. Actually, that is the show. And Tom, thank you so much for your comment. A copy of Music to Code By is on its way to you. And if you'd like a copy of Music to Code By, write a comment on the website at .netrocks.com or via any of our social media, because we publish every show to Facebook and Google+. And if you comment there and we read it on the show, we'll send you a copy of Music to Code By.
And definitely follow us on Twitter. He's at Rich Campbell. I'm at Carl Franklin. Send us a tweet. We try to observe them, but they keep slipping away.
You can observe them, but then you'll know where they are.
Oh, sorry. That's bad.
Is it going to be all quantum humor the rest of the day?
No, that's it.
Okay, you're done. That's all there is.
No, I can't promise. All right. Well, John Azariah is here, and we're going to talk to him about Q#. Let me formally introduce John. He's a frequent speaker at conferences on various topics of expertise, including functional programming, cloud computing, computer science, and software engineering. He's got over 25 years of experience writing all kinds of software, from packaged applications like Oracle Forms, Microsoft Excel, and Microsoft Project, tools like Bright Sword Designer, websites, web and cloud applications like MYOB account right. How do you say that?
MYOB.
MYOB.
Mind your own business.
Yeah.
MYOB.
Yeah.
Thank you. Account right. Microsoft Azure Batch also. He currently works for Microsoft Research and leads the effort for the new quantum computing language, Microsoft Q#. Welcome, John.
Oh, thank you.
That's quite a pedigree.
So you might know your way around Q#.
I might.
A little bit.
Yes.
Just a little bit.
Just a little bit.
Do you still relate to that comment about we're still feeling around for the real transistor of the next generation computer?
Well, yes. I mean, to be honest, we haven't got a qubit yet.
Right.
And the people who do
Wait. We have to just sort of back up and define some terms here, because I, for one, am completely lost when it comes to quantum computing, even after talking to him.
Mm-hmm.
Right.
So qubit.
Qubit. Quantum bit.
Okay.
Okay. Now, we're used to a von Neumann architecture, the standard computer,
right,
where memory is stored in RAM and disk and all of that in binary format.
Can I ask you to pull this up a little bit?
Certainly.
Yeah.
Absolutely.
I noticed that.
Is that good?
It just slipped down, that's all.
Yeah, you got to rotate around your ear.
There you go.
These are the perils of recording podcasts.
But it's great that we're in front of each other and can see this.
Yeah.
This is better?
Better.
Better,
Sweet.
yeah.
So what is a qubit anyway?
So in standard classical computing, right, we have memory which is sort of stored in RAM and on disk and all of that.
Right.
And then you have these processors that are basically also transistors. I mean, memory is stored in transistors, and the processor is also a transistor, set of transistors that build up to form flip-flops and then adders and
you make an AND gate, you make an OR gate, you make an exclusive OR gate, like
all
these fundamental
all that fun stuff. And then you bring the memory in, and then you operate on it, and then you write the memory back, and you do that kind of thing.
Right.
Yeah.
Quantum mechanics is a little bit funny. So what happens here is that you need to, when you want to operate on something quantum mechanically, nature doesn't let you observe all of the innards of the quantum mechanical state.
Right.
So you'll end up with a system that both holds the state in a way that you can't actually see it, and also operates on it.
Right.
So a qubit is both the processing unit and the bit of memory that stores the state in there.
Okay.
And so when you want to build up a bigger system, what you do is you take multiple qubits together and you kind of fuse them together. And I'm being super technical here.
Entangle them?
Tensor them, really.
Okay.
And some of the fusing is entanglement. Some of it's just tensor product of the qubit states.
Okay.
And then you land up with a state that is actually going to become twice the size every time you add on a qubit. And because the amount of information that's stored in an n qubit system is actually very, very large. It's what is technically known in the term as a very high dimensional linear space.
Okay.
It's a vector in this very, very high dimensional linear space. You can't actually ask for the vector in order to do something with it. You take the system and you say, hey, please rotate this vector this way, or whatever it is. And so the system of qubits is both the state storage and also the thing that actually operates on the state for you to do something.
It's the accumulators.
Yes.
So the burning question in my mind is, do we have to have a quantum computer before we can have a language that can program in that paradigm?
Well, yes, of course. I mean, no, actually, it's the other way. I should, edit this out.
There you go. Let him ask it again.
So the question in my mind is, do we have to have a quantum computer before we can have Q#?
Oh, absolutely not. Because the way in which we think about quantum computing is it's actually levels of abstraction, right? So what you said earlier about classical computing before transistor, people still had the idea that there was such a concept of computability.
Yeah, Ada Lovelace basically outlined what von Neumann would ultimately coin as the machine.
That's right.
In the 1800s.
Yeah, that's right. And in 1920 and the early 1930s, there's a formal theory of computability with Alan Turing and all of that that actually talked about not just, hey, what are the nuts and bolts that you need to do the computing with, but what does computing actually look like, and what kind of problems can we solve with computing, right? And they did all of this stuff before they had the very first sword program computer possible.
Yeah, if you talk about what Turing and stuff doing, they were hardwiring computational engines. The Bomba was exactly just a hardwired computer. And you didn't require the transistor. as I understand it, there are different kinds of qubits. Like there's several approaches to building a qubit. I'm thinking about D waves, quantum annealing.
Sure.
And MSR, I think you're working on a fermion-based qubit.
Right. So
these are all software models, right?
Well, these are the hardware. But I'm just curious as to where you're at on all of that.
Right. So let me just back up 1 second, though. What if you think about what computing was like before the transistor? It was basically the mathematical model of computation.
Right.
Was the important thing, and then you could basically build systems and even talk about algorithms just based on the mathematical models. So in a quantum computing world, it turns out that the mathematical model of quantum computing is a generalization of classical computing.
Okay.
And the generalization is actually linear algebra, not anything else. So if you had linear algebra with certain restraints and so on and so forth, you can actually build up a viable, consistent computation model for quantum computing. And then you can embed that into an emulator, which is kind of what everybody does these days.
And like an emulator, it's just not as fast as the real thing?
Absolutely not. Okay. It's orders of magnitude slower, enormously limited in terms of how much you can
just like the Android emulator.
Yeah, right. So if I can just kind of wrap my brain around this. So you have software models that emulate what the hardware will do when we have a quantum computer that we can run it against. But in the meantime, we can develop architectures and programming models and languages like Q#
and algorithms,
that we can do so that when the hardware comes around, we've got software to run on it.
Yes, exactly. Yeah. And the hardware will take some time coming.
Sure.
People have been working on different types of hardware for a very long time. And as you mentioned earlier, there are many ways to skin this cat. So you can create, and that is actually a quantum joke.
Little Schrodinger reference.
Yes, okay. Since you guys didn't laugh.
That's thinking out of the box right
there. There you go. Well done. Well done.
Well know if the cat's alive or dead.
Well played.
Cat's out of the bag.
So there are many ways to actually build qubits. And what a physical qubit really looks like is really a quantum mechanical system that has certain properties. And there are many quantum mechanical systems that are out there in the world that kind of have some of these properties. And the trick is to get them to actually be used in a computational manner.
Right.
And so we have, the front runners in the field who have these things called transmon qubits. People like IBM and a company called Rigetti, and Google just announced a 72 qubit device. People are basically talking about a 144 qubit device coming out soon.
Right.
And so on and so forth. These qubits are interesting. They are real. They have the quantum mechanical properties. They are severely limited with the kind of characteristics that they have. So for example, these are devices that show all the quantum mechanical properties that you need for about 1/1,000,000th of a second.
Okay.
And so now you have to basically sequence your instructions to interact with the quantum mechanical state of the thing, and you don't really have much time to do it. Now, in order to make things a little bit more tractable, what you'll end up doing is introducing error correction, again, a mathematical model for it. And that effectively allows you to have, between hundreds and tens of thousands of these little physical qubits that you can now simulate a logical qubit that has a lifetime that is tractable.
Right.
Or you could take.
This is why the numbers are so large, because wasn't the magic number for quote real qubits? It's like once you get to 30, you're going to be good in terms of complex computation.
Well, no, that's a different story, and there's quite a contentious issue to be discussed at that point, because there's this really weird phrase called quantum supremacy that people talk about,
right?
Which is notionally the kind of thing where what is a problem that I cannot solve classically that I can now have a solution for from a quantum mechanical system, to say that this quantum mechanical system is actually better than the state-of-the-art classical stuff.
And aren't there certain sort of classical equations, like this is essentially unsolvable with traditional hardware, it'll take the duration of the universe to solve it, but quantum should be able to knock it out, and it's going to be one of your proofs.
Well, and there's an enormous amount of research in trying to find the smallest solution that requires the fewest quantum resources that still prove that the quantum mechanical approach is superior to the classical approach. And the jury is still out on which problem is going to exhibit this behavior in the first place.
And can I ask about the D-Wave guys? Because their system seems different.
It is.
And somewhat contentious as well.
Well, not contentious. Look,
who is that?
This is another company making another kind of quantum computer, but they're advertising 1,000 qubits.
Well, I think they've said something about 2,000 qubits, but really what they do is they're not actually. So there are two models of mathematically describing quantum computing. One is called the gate model, which is effectively a time evolution of quantum state using matrix multiplication. Okay? And another one is what D-Wave does, which is to try and find the lowest energy of a given system that represents a problem. And by finding the lowest energy, you kind of get this simulated annealing kind of approach to finding an optimal solution for something. Okay? What's contentious about this is that this approach is not quantum specific. It is quantum annealing has been around since the 1950s. And it turns out that you can actually use the mechanical approach, quantum mechanical approach that they've taken, and optimize your classical algorithm to come up with the same solution with far less resources from a classical side. So this thing happens to there's a constant there's an arms race in some sense going on where somebody comes up with, hey, this is a quantum system and it solves this problem fast, and then someone takes quantum inspired optimization to a classical sense and then beats the classical problem around the head a bit, and then you'll end up with a classical solution that actually outperforms the quantum one. And this has actually happened more than once. So for example, the quantum optimization that D-Wave achieved was actually first replicated by an Azure cluster. So several orders of magnitude cheaper, $2 million to $2,000. And then after a little while, somebody worked on it for a graduate project or something like that, and eventually landed up getting the same result on a laptop. So this is the reality.
And that was one of the conversations that I saw going on around these things, was that you weren't demonstrating the benefits that we expected from quantum in this approach. It was still just reasonably solvable problems.
But that's the annealing model that D-Wave uses, which isn't the gate model that all the others are actually working on. And the gate model allows you to actually employ certain interesting algorithms. So in the 1970s, there was a brilliant chap at MIT called Peter Shor, who came up with the algorithm for factoring numbers, And factoring numbers is hard, and should be. I mean, that's why we have credit cards that we can rely on.
This is the basis of most encryption is number factoring.
The entire world's economy, if you want to be less melodramatic about it.
That's the left. Okay.
So basically, if you want to destabilize the world's economy, you want to learn how to factor numbers quickly.
Factoring large primes is a great way to wreck the economy.
Exactly. So so Peter Shor basically used number theory and a whole bunch of basic mathematical stuff to come up with a mechanism to reduce the factorization problem to the problem of period finding. As in, I give you a function that spits out a bunch of numbers. Tell me if this function is periodic, And that turns out to be a hard problem, classically as well, if you think about it. But it turns out that the two are related. The period finding is now basically factorization. The two are equivalent. And so the brilliant bit came to using quantum mechanical techniques to achieve speedups on the period finding piece. And it turns out that takes exponential time classically and linear time quantumly.
And so this should be the iteration, is that as you increase the complexity of that expression, the performance on classical computing is going to drop like a rock. It's going to go terribly slowly, and the quantum should be unaffected.
So what we can take away from this is once we have quantum computers, the whole world's financial instability is
that's a fairly
going to collapse, right?
You wouldn't want to be dramatic or anything.
No. And you wouldn't want to be inaccurate either. And And so before anyone goes off and shorts Bitcoin, right, saying this whole thing has gone to hell, let me hasten to point out that not only is post-quantum crypto a real thing, but we already have solutions that are resistant to crypto quantum attack.
Okay, I want you to hold that thought right there.
Sure.
As best you can, for me anyway, while we take this moment for a very important message. All right. And we're back. It's .NET Rocks. I'm Carl Franklin. This is Richard Campbell. This is John Azariah, and we're talking quantum computing. Well, they're talking quantum computing. I'm just sort of bewildered. But
you know, one of the things that I'm reminded of here is with this taking of these quantum ideas and applying it to classical computing into benefit is the same thing we saw with functional computing with F#, where functional programming practices could be applied in C# and made some nice code. You could write very functional C#, but it was only apparent when we started having functional hanging around with us all the time that you started seeing those practices. So I'm intrigued that there's a similar comparison, that these way that we think about quantum computing is influencing classical computing.
Indeed. I mean, and to be fair, I mean, let's put the crypto thing on hold for a minute,
sure,
but I'll come and address this specific thing, right? And to be fair, classically we've been taught algorithms in a particular way, and the algorithms have usually been taught very pragmatic, set theoretic maybe approach, whatever it is. But usually you don't go all the way down to linear algebra and matrix operations and that kind of thing, all the way down to the nitty-gritty of what you're really doing is manipulating vectors in large Hilbert spaces. But it turns out that that's actually how quantum mechanics works, and as a special case, that's actually how classical computing works. It's something that we don't start with the association early. So it's not surprising that you get insights from working with quantum computing in this deeply mathematical approach, and it suddenly dawns on you that the special case of classical computing is really a special case of this deep mathematical insight that you've received.
Right.
And now you can apply that classical things, and all of a sudden you have better understanding of what the classical behavior is like, or how to improve the
Is it providing an insight?
It is.
It's because you're exploring the special case in more detail.
Correct. And it's a different way of looking at it, because you can't look at quantum mechanical systems intuitively. There's nothing intuitive about the quantum mechanical system.
That's an old Dawkins line. If you feel like you're understanding quantum computing, you're further away than ever before.
Hey, I must be making progress.
Yeah, we're all making progress. So in terms of the quantum crypto, though, post-quantum crypto is a real thing. We already have solutions for it, even at Microsoft, and we're already rolling stuff out. So
you're starting to think in terms of, given this ability to factor large primes quickly with quantum computing will disrupt this style of encryption. We have styles of encryption that can resist that?
Indeed.
Okay.
Indeed. And there are styles of encryption that are much more difficult to crack, even if you do have a quantum computer.
Right.
Right? But
are we just going up to larger primes, or is it a completely different strategy?
It's a completely different strategy.
Okay.
Usually it's things like lattice-based encryption and all this other stuff. So it's interesting.
Those are a lot of theoretical pieces we just haven't cared about, because the large prime strategies work so well, and they were inexpensive to compute.
Yes, and basically it was a matter of nobody bothered to try and figure out whether they needed a better mousetrap, because the mouse was already dead.
Well, they called it PGP, pretty good privacy for a reason, right? It was pretty good.
It's pretty good.
And then now it's not. Now we have a threat that it may not be.
Well, to be fair, we are some way away from it being a threat.
I agree.
And to underscore the second point I want to make, which is, whilst encryption is actually the big ticket item that you think about as being
this is the magic thing that quantum will
solve, there are several trillion-dollar problems that will be solved when you have a fraction of the number of qubits that you need to solve encryption.
Interesting.
Okay.
There are more valuable things for less cost available.
Indeed, and which we will meet as canaries in the coal mine long before you get to the point where you break encryption and destabilize the world economy.
Right.
You might actually do things like solve world hunger or solve carbon capture.
Right.
Then you won't need money.
Right. So, well, there you go.
Well, I would think solve plasma instability in fusion reactors so that we can actually get those things off the dime.
Well, so that particular application isn't something I'm familiar with, but I will tell you I'm very familiar with the problem of solving hunger.
Okay.
And I can give you a 2-minute introduction to what that looks like.
Yeah, please.
I'm really curious as to how quantum computing would affect that.
Right. So let me take you back to 1911.
Okay.
Okay. Before that, we didn't have industrialized farming. So you were dependent on natural ways of fertilizing the ground.
Bat guano.
Right. Bat guano is one of them. Another way of interestingly solving that problem is to grow beans.
Yeah.
Right?
Nitrogen fixation.
Nitrogen fixation by plants.
Yep.
Right.
So you take the plants and then you till them into the ground and you've got fertilizer?
No, you don't even have to do that. You just have to grow beans in a field.
Yeah.
Okay.
Field that had been growing wheat, you now grow beans, and the difference in the plant actually is driving nitrogen back into the soil.
Indeed.
Great.
You can now harvest the beans.
Okay.
And then plow it down and then grow corn again.
Right.
No problem, right? The way that works is like this. In the root of the bean plant, there are parasitic nodules. These have nothing to do with beans. They just happen to live on the bean plant, right? And inside those nodules, you have bacteria that live in the cell membranes in an anaerobic environment that know how to capture nitrogen from the atmosphere and hydrogen from water, put them together and form ammonia. Okay? That is a profound, complex chemical reaction.
Yep.
In 1911, we figured out as humans the first way to actually make ammonia from atmosphere and water. And that's the Bosch-Haber process.
Right.
And that looks like nothing like what the bean plant is doing, right? It looks like taking nitrogen, heating it to 5,000 degrees, putting 50 atmospheres of pressure, sticking a whole bunch of catalysts in there, and ultimately getting ammonia, right? We haven't changed much since 1911.
No, it worked pretty well. Makes great gunpowder too.
We spend 4% of the global energy output on just making ammonia.
Yeah.
It is the most important industrial chemical on the planet, right?
Because it makes fertilizer. It's the reason we feed people.
Because this is literally how we've eaten anything that we've ever eaten in our entire lives.
And explosives.
We talked about this in the Agriculture Geek Out, right? That the green revolution in the 60s, where we went from 1 billion people in the early 1900s to 3 billion people, where we should have tipped over as a civilization. It was this process and that technology that allowed us to triple our population and not have everyone starve.
Yeah.
Yes.
Yeah.
Now, why do we not do what the bean plant does industrially? And the reason we can't is because we don't understand how nitrogenase, which is the enzyme that's used by nitrosomonas bacteria, the bacterium in there, we don't understand how nitrogenase works from a chemical perspective. Like chemistry, we can't sit down and say, hey, this is actually the set of equations that you need to solve to figure out how nitrogenase works. And when nitrogenase meets this is how it catalyzes this nitrogen fixation issue. We can't do it in the lab in vitro because everything's in an anaerobic environment inside the nodule, right? And we can't analytically understand the chemistry.
Is this a protein folding problem?
This is not a protein folding problem. This is typical chemistry where, because we have a transition metal in the block we have 2 transition metals, in fact, in nitrogenase, we have iron and molybdenum. You have to solve the problem of what happens to about 170 electrons in order to get the understanding of why nitrogenase has these properties.
It's like a nanoscale catalytic behavior.
It is nanoscale catalytic behavior.
Yeah, that is really cool.
Okay, but
hard problem to solve.
Very hard problem to solve. So much so that if you tried to sit down and classically write out the state of an electron
on all the permutations.
Yes. Yeah. In water, for example, there are 2 hydrogen atoms.
Yep.
So 2 electrons from the hydrogen atoms and 2 from the Cooper pairs on oxygen. So 4 electrons. You can sit down and solve the water problem analytically. It'll take you a couple of weeks, but as a grad student, you can probably sit down and work out the equations and say water will have these properties.
Right.
Right. At 170 electrons, each electron's waveform takes at least 2 complex numbers to store. To store 170 electrons characteristic waveforms, you need 2 to the 170 complex numbers.
That's a big number.
How big? There are only 2 to the 150 atoms on this planet. So if you made every atom on the planet RAM
part
cell,
of the equation,
a RAM cell,
yeah,
you would need 1 million Earths just to store the problem's definition.
Nice.
Right? So classically, we can't solve this problem.
You should wait for the iPhone 40.
Yeah. Yeah, I think you're a little pessimistic here, right? Like, we can't solve the problem because we don't have enough atoms.
Jeez.
It's such a small thing.
I order them on Amazon.
Nice.
Well, Richard.
Yeah, buddy.
Guess what time it is now?
Must be that happy time again.
Yeah, that's right. It's time to decouple the Heisenberg compensators, split the Freem blazerator into its component parts, and dispatch the Quirkadirk so someone around here can get a stronger coffee last week.
Nicely done.
That joke got funny at last week. That's when you nailed it, man. That was beautiful.
Thanks. It's actually time to give away a $200 Amazon gift card, compliments of Progress Telerik, to one lucky member of the .NET Rocks fan club. But first, let me tell you about the most comprehensive developer toolkit for building modern apps on the market today, Telerik DevCraft. With more than 1,100 Telerik.NET and Kendo UI JavaScript components and controls, you can easily build modern, high-performant web, mobile, and desktop apps, as well as chatbots. The toolset also includes reporting solutions, automated testing and productivity tools, and comes with a range of support options. New this year is a free online training program for all license holders. So with this, alongside thousands of demos with source code, comprehensive docs, and a full assortment of Visual Studio templates, you'll be up and running with the Progress Telerik and Kendo UI tools in no time. Download a free 30-day trial today at telerik.com/download.
All right, buddy. Who's our winner?
Today's winner, Richard, is Buck Hicks.
Congratulations, Buck. Big clap for Buck. Ain't no golf claps here.
And Buck just won a $200 Amazon gift card, compliments of Progress Telerik, just for being a member of the .NET Rocks fan club. And if you'd like to be a member, go to .NETRocks.com, click on the big Get Free Stuff button, answer a few questions, and join the fan club. We have thousands of members all over the world. In every show, we like to give away stuff from our sponsors. And every December, we give away a $5,000 technology shopping spree to one lucky member of the .NET Rocks fan club. But you got to sign up to win. Hey, and by the way, if you want to support .NET Rocks and the fan club, go to patreon.netrocks.com and make a pledge. We also like to ask our guests, John, if you had $5,000 to spend on technology today, what would you buy?
Not a quantum computer.
No. You know of a $5,000 quantum computer. I'd like to know about that.
Well, look, this is a good question because back in the day when I was a little kid growing up in India, there was a lot less light pollution. I spent a fair bit of time looking up at the stars.
Yeah.
Haven't done that in a long time. Would love to get a good telescope and a decent camera and try and put
and $5,000 will get you a nice auto tracker.
That's right.
You literally plug in what you want to look at, and it'll turn to the right location and track for you as the planet rotates. Like shiny.
Yeah. So that's probably what I would do.
Yeah.
I'm gonna get my own little observatory going.
That's a great idea. I love that.
I took my first photo of, at the first saw it this week, the Southern Cross.
Oh yeah, right, because we're down here.
Yeah.
There
and
it is.
when you see the Southern Cross for the first time, you understand now why you came this way.
That's some lyrics, I think. Yeah.
Crosby, Stills, and Nash. Anyway, I took my first star picture with a DSLR.
Fantastic.
With your ADD,
yeah, and it was great.
It's good fun.
So I don't know, the telescopes they have now, you can connect to a DSLR camera, so you can not only take great pictures, but they can actually have some detail.
Yeah, really good stuff. I'd love to jump back into this because I now have a picture of what John thinks is an intractable problem. Once you're using up all the atoms on the planet many times over, that's what we call hard.
Yes.
And so, knowing the quantum computing models, this is the kind of problem we take on. It's actually a very, very small problem. Understanding an enzymatic behavior in a plant is beyond our current computational abilities. These machines could take that on.
Well, it's actually interesting because if you think about it, this is actually Feynman's idea Feynman basically came up with the profound insight that said, hey, the math about this, the mathematics is hard, right? But nobody told the bean plant this.
Right.
And it's solving the problem without
you know there's a solution.
There's a solution.
Yes.
All you have to do is figure out how to get that to do the computation for you.
Right.
And in some sense, that's exactly what quantum computing is. You take the quantum mechanical natural phenomena that's present and happening already, and you leverage that by making your problem expressible in terms of the quantum mechanical behavior, so that you get nature to solve the problem for you.
When my boss told me that I didn't know beans, he was right.
He was absolutely right.
He was absolutely correct.
Turns out nobody knows beans.
None of us
knows beans.
Knows beans. So don't feel so bad.
No.
I want to get back to the idea of the currency problem, because it seems to me that when you have a technology that can undo a system, you also have a technology that can redo that system with more robust results. So before we get to the point where encryption fails, maybe we could get to the point where we could encrypt with quantum computing at a stronger and create a stronger thing, so that a quantum algorithm couldn't untangle it. So to speak.
We have that. That's exactly what we have, and you're absolutely right. In fact, I'll go stronger than that. I'll say that the encryption doesn't need a quantum computer. The encryption that will be resistant to a quantum attack can be done classically.
Right.
Oh, okay.
And again, it's that sort of thing, because we've been exploring the quantum problem, we suddenly see that vulnerability in classical computing and can come up with strategies that resist the quantum problem.
Indeed, we already have strategies that do
the lattice.
The lattice-based encryption, and so on and so
one
forth.
of these days, I'm going to go to Europe. I'm going to try to use my American credit card, and they'll say, "Oh, I'm sorry, you don't have the quantum chip."
Yeah. Nice. Well,
quantum resistant chip.
Nice.
Maybe.
Okay.
Yeah.
We really haven't talked a whole lot about Q#.
No.
I'm wondering if, again, we have this opportunity to start writing these expressions, even if we can't necessarily compute them. Like, could we get to a place where we can code a model around trying to understand these nitrogen fixation strategies, and we're not going to be able to run it, or you can run it, but it's never going to finish until we have the machine that can actually do it.
Indeed. I mean, so because we're really talking about modeling computation, what does quantum computing look like? It's actually very much like programming against a graphical CPU.
Sure.
Right? It's a GPU kind of thing, as in the GPU knows how to do certain types of operations much better than the classical computer can.
Sure.
So you ship the quantum piece off. You ship the GPU piece off to the GPU. In the case of a quantum mechanical system, you ship the quantum computing to the quantum computer.
Right.
Right? And so now comes the interesting bit. Now, if people who've done CUDA realize that the host language is in C++ or whatever it is, you write the you write the graphical piece in the same language, and you just ship it across. And somehow there's some black magic that happens, and the bit that's supposed to run on the GPU runs on the GPU, and the bit that runs locally runs locally.
And you may have done this fast for the listener. CUDA, it was a programming space specifically for GPUs. It's been around for a number of years now.
Yeah.
But it was good at these tensor array type problems, because you've got the GPUs are really big, are small scalar processors, lots and lots of them.
Yes.
And they're the same way that you want to create a shadow on an object in 3D space it's great for a tensor math problem. It's the same kind of problem. You want many values applied simultaneously across a large number of numbers.
But more so than that, I mean, when you have an adjunct coprocessor like the quantum computer, well, it turns out that computer can't actually live on your card inside your own box, because one of the quantum mechanical systems, one of the quantum mechanical properties that you need to sort of exploit is the fact that if you want to hold on to the state inside the qubit, you have to isolate it as much as possible from the environment. And so you typically do that by chilling everything down.
Right.
And so your typical quantum machine at least the approaches that we've taken so far, tend to work in the neighborhood of 15 millikelvin or so.
Right, living in a bath of liquid helium.
Well, no, liquid helium is far too warm. Liquid helium is 4 Kelvin.
Oh my goodness.
We are talking about 15 millikelvin, which is about 15 thousandths of a degree above absolute zero.
That's awfully chilly.
Right.
Wow.
So, in fact, the engineering challenge
don't stick your tongue on it.
No. the engineering challenge of sticking a wire with one end at 4 Kelvin and the other one at 15 millikelvin is actually significant.
Sure.
Yeah.
Right?
Yeah.
And so anyway, the long and short is that the quantum machine is likely to live in such an exotic programming environment or such an exotic environment that you're unlikely to keep one in your basement.
Yeah, no, it sounds like a product you'll take from the public cloud.
Indeed.
I'm trying to imagine the syntax of Q#, and I'm having a real hard time. So does it look like a traditional programming language in the sense that you're using numbers and values and
yeah, that's an interesting question. Just hold that for a moment, because I'm going to come back and tell you why you need a language in the first place.
Right.
Yeah, good.
Right. So there are people who have actually built qubits, companies that have qubits, that allow you to actually interact with them over the cloud. This is already a thing.
Right.
Right. So there's IBM and Rigetti and all of these places where you can go and sign up for an account and schedule a job that says when you're done, when my turn comes around, run this thing on the 5 qubits that you've got and give me the result. Right. This is actually a thing you can do today.
Okay.
But the way they do it is by writing the program in Python and calling a library function, which then gets an implementation for doing something on the device.
Okay.
Right.
So there is a function you call from Python that will run on the quantum computer.
Correct.
And there's some kind of expression inside of that function?
Well, no. I mean, the function is literally the thing that you want to do. Okay. So you'll end up retargeting from against a simulator or running it on the hardware or whatever it is. Having just a plain old library plus host language is a very naive way of doing it. It turns out that we at Microsoft are quite good at building languages.
No.
We've done it for a few times.
A couple of times.
A couple of times.
Here and there.
And one of the things we noticed was, look, in order to make it so that the program that you write that's supposed to run on the quantum computer is something that we can reason about, optimize, and actually prove correct. So being able to have a strong type system, or having a sensible way of actually composing pieces together from libraries that somebody's written with code that you want to write, and so on and so forth, being able to share this information out so that we have distributable algorithms, for example.
Right.
It's useful to actually model that as a programming problem in its own right. And when you do that, it turns out that it's far simpler to model a domain-specific language that expresses the quantumness in a quantum context.
Okay.
And run it in the context of a host program, just like a CUDA program would be. You have a host program, and then you say, oh, and this piece is the quantum bit. In the old world, when I did CUDA programming, you start that with a comment that says, this is the hard bit.
Here comes the hard bit right now.
This is the hard bit, and now I've done this stuff in CUDA.
Right.
Which is effectively what you're doing here is you're saying, well, this stuff is in quantum, so I'm not even going to try to run this classically.
Right.
I know this piece is going to be written in a different language with its own type system, its own mechanism of function composition and all of this other stuff. And the compiler that runs that can now optimize it against the actual device that I'm going to run, because I don't know what instructions are going to be primitive going forward. And so the levels of abstraction basically give you specifically the answer to the question that you asked earlier. Can we do this without a quantum machine? The answer is emphatically yes, you can. And in fact, not only can we do this, but we can do it in such a way that when a quantum machine becomes available that is different from another quantum machine that's already there, you won't even know the difference.
You'll write a new abstraction for us.
Yeah.
So is this very much following the .NET model of Q# is an abstracted language that sits on top of a kind of IL that then goes through a runtime that will be specific to a given machine?
Yes, and specifically that will be an exotic computing environment that is non-von Neumann in nature. So even the instruction set that we put as an abstraction over the quantum device is going to have to be something quite significantly different from anything that we've seen so far. But we've done this once, and we have a few ideas on how to do it again.
You've done it a bunch of times. I mean, for research I've done, you think about how many times they've implemented IL to compilers, not only when you think about 32-bit versus 64-bit inside of Intel-style architectures, but also the ARM implementation, the Itanium implementation. Like they did this many times, and some that we never saw publicly.
Yeah.
There were processors that were being played with, and Microsoft did development to make sure that .NET developers would be able to compile against them. They just never shipped it. And this is another example of that.
Indeed.
And someday we'll be able to run Windows 95 as an Electron app on the quantum computer.
Who would do that? Andy will do that.
Yes.
Maybe. I think is the correct answer. There you go.
Because I really want to play Minesweeper, but I remember in 1995 it was pretty slow. You know, you click that thing and then it would think for a millisecond and then boom, it just explode.
Yeah, so that's kind of the approach. And having the language allows us to now distribute a library that's written in the language that is completely agnostic of what kind of hardware you're going to need.
As far as we know now, I mean, the hardware could get really weird.
Hardware will get really weird.
Yeah.
We're counting on it.
Yeah.
But the algorithms that you are going to use, we know how to add two registers together from a quantum perspective. That's not going to change. What will change is what are the primitives that this new hardware gives us, and how do we leverage that without you having to rewrite everything?
Right.
And that will actually come clean the moment we start moving forward.
So if you describe now, because getting back to the language and the syntax of the language, if you describe it, will anybody have any idea what you're talking about?
Absolutely.
Okay.
So strangely enough, I mean, this is one of the languages that has been influenced by many of the languages outside in the world today. So we borrow ideas from F#, we borrow ideas from C#, we borrow syntax from C#, we borrow a couple of interesting ideas from Python. We've created a new concept from a type theoretical perspective, just from experimentation. So we have the ability to actually draw on language design and category theory and type theory and all of the foundations from other language design spaces. And that's kind of how we came up with Q#. So if you look at Q#, it looks like C#. It looks suspiciously familiar. It is stateless. Because if you think about it, it's precisely because you can't represent the state in a classical sense that you need to have this language in the first place.
What do types look like?
So types are tuple-based.
Okay.
And we have types that basically have arbitrary arity tuples.
Okay.
And a function is always a single tuple in to a single tuple out.
Okay.
But the arity can change. We have partial application on the types, on functions that allow us to provide more than one default argument. So it's non-curry based if you want to think of it from a functional perspective. When you curry or you partially apply, you can only do one argument at a time.
Right.
You can have a tuple where you provide the first, the 7th, the 18th, and all following arguments, and leave holes for the rest of it, and it'll return you a function that takes only the holes and then plugs it in. So it's a non-curry based partial application approach.
Right.
Generics are supported, so we have our own generic system that allows us to do type calculus. We have, as part of the quantum context, the need to be able to apply functors on what would have normally been simple arrows in the category theoretical sense. And we actually generate functors for certain types of algebraic operations. So for example, when you want to calculate the adjoint of a sequence of operations, which is a mathematical thing, you don't have to write that out, where you would have done if you just used library calls in Python. You would have to manage what the forward operation was and what the reverse operation was. We can deduce the reverse from the forward because we have a compiler, and we can generate that for you. So from a category theoretical sense, there's a lot of foundational work that's been put in to make it robust, sound, and reasonable, so that when we look at a piece of code, we can reason over it, do whole program analysis, and say, when I call this function in the context of another function, it generates this sequence, and I can reduce that sequence down mathematically, which is something I could not have done if I just knew this piece, because this might have been written by somebody in a library that I don't have the source code for. And they obviously don't know what context I'm going to call this library function in. So how do you actually optimize the two pieces together without knowing, when they're separated by time and space, really.
Right. Well, that was componentization strategies in the first place, right? Encapsulation was supposed to create those isolations where only the interfaces mattered.
Right.
Is that just not going to work the same way in a
No, it's not,
space?
right? Because here you actually care about the optimization of the sequence.
Right.
So this thing results in a sequence, this thing results in a sequence, you're putting the two of them together, and now, in a special case, these two sequences actually can be combined in some particular way. You won't have any clue of how to do that unless you can run an optimizing compiler on the compiled version of this thing.
Yeah.
And that is actually what Q# is excellent at. It's actually
that is a uniquely quantum problem.
Indeed.
That's really cool.
So I'm having a hard time understanding. You say it's a stateless language, so aren't variables state? So if you have types, you have variables. Isn't that a state?
Yes and no. So the quantum state of the thing is actually an opaque type because you don't know anything about the state of the quantum system. If you were able to represent the state of the quantum system, you wouldn't need the quantum computer in the first place.
So you can write variables, but if you read them, they change?
Well, debugging certainly doesn't work the way you expect it to. We broke Visual Studio.
Because if you can set a breakpoint in a quantum state, we get to decide exactly what happens to that cat.
That damn cat again.
So observation is actually quite an issue. I mean, we can observe in a simulated environment and say, okay, look at the state vectors and stuff like that.
Yeah.
But in the real classical quantum computing interface, you can't possibly do debugging the way printf debugging won't work even.
Right.
So nothing will work the way you expect it to work, right? When you say variables,
kind of spooky.
When you say variables, we don't actually have variables. We have bindings that are constant and immutable. And really what you're passing in are arguments that you can then carry away.
So the arguments are what you start with, you just put them in, and then there's no reading them. The things happen. And
the things happen. So in effect, what you're saying is if I want to start with a qubit in the 0 state, which is what happens when you ask for a qubit, even down at the silicon level or whatever it is, it'll tell you, okay, I've now given you a qubit. All you know about the qubit from the Q# program is my ID is 12.
Right.
Right? You don't know anything about what state qubit ID 12 is, because if you did, you wouldn't need the qubit in the first place.
Right.
Right? And so what you would do is you would then say, hey, to qubit 12, please rotate it this way, or please rotate it that way, or run this sequence of operations on that qubit. And you can define which sequence of operations by using some variables, and that makes sense. Or you can iterate over things in order to generate the sequence of operations that runs on the thing. But you're always talking about what you're going to do to the qubit rather than what the value of the qubit was after you did something to it. So the state of the qubit is always opaque as far as you're concerned. So it's a stateless language.
So let's say we have a quantum computer and we have Q#. Am I able to basically send a stream of information anywhere in the universe by quantum entanglement?
So entanglement doesn't work like that. Entanglement is, strictly speaking, a mathematical operation that takes more than one qubit and makes them non-independent of each other.
Yeah.
So correlates them somehow.
Right.
Now, what you can do with the correlated qubits is actually kind of interesting, and kind of spooky. Right?
At a distance.
Yes, at a distance, right? But it doesn't beat any known physical laws yet. Right. We don't know that. We can so far haven't broken the speed of light communication, for example. Right? And I think there's a proof that you can't. So if anyone comes and tells you that you can, I think
they have to present you with new science to do that.
By definition, we say your experiment is wrong.
Yes.
Right? And then we talk about...
It's that or the universe is wrong. Let's
something
pick.
like that. It's the same thing as quantum algorithms. Another misconception that's quite common is that we'll run NP-complete problems differently. I think the accepted reasoning at this point is if you have an algorithm that seems to prove that NP-complete that P equals NP, for example, then it's almost certainly that you have a problem with the algorithm.
Right.
That's not to say that we're blind enough to say that we'll never be able to know whether P is equal to NP or not, because that's still an open question, right? But I don't think while there are several really disruptive and really profoundly different, non-intuitive things that quantum mechanics gives us, I don't think fundamental laws are actually under threat yet. We don't actually know.
Right.
So signal R is out of the question, what we're saying.
Yeah,
Quantum
no,
signal R.
I don't think so.
Yeah.
Sorry.
Not going to go that way.
Well.
Any sense when we're going to start having these machines to work against?
Oh, beautiful. We have some.
Yeah.
We have the noisy qubits that are out there already. In fact, they're out in such numbers that people have started a new branch of quantum computing called NISQ, noisy intermediate scale quantum computing. As in, you have hundreds of qubits that don't last very long. Can you do something useful with them?
Right, and
that's
there's a lot of error correction involved in there, discarding incorrect values.
Maybe, or maybe we say that the only things that you can actually do are just one or two operations, but combined with a large number of qubits, we can do something that we couldn't do classically. There are people thinking about that.
Right.
Microsoft is not actually thinking about NISQ at the moment. We're still trying to get our first qubit. And that sounds like we're behind the 8 ball a bit, and it's perfectly reasonable to feel that way. But the physics behind the kind of qubit that we're going for actually has higher promise than the other approaches. So ideally speaking, when a topological qubit comes forth, when it does, it should actually have characteristics that make it immune to certain types of interference and certain types of decoherence. So the first qubit that we build, or the first real qubit, topological qubit that we build, will actually have lifespans that are orders of magnitude larger than the existing ones.
And become much more computationally relevant.
And become much more computationally relevant. So the idea is that someday, possibly in my lifetime, we'll put 1,000 to 1,000,000 of them on a 1-inch by 1-inch wafer, chill the thing to 15 millikelvin, and do something interesting.
Right.
Right? But more pragmatically, the stated goal is that we should get the first topological qubit by the end of this year. We're still on track. We haven't announced anything to the contrary yet.
Right.
That said, we've...
This show's coming out after Ignite. Who knows what you guys might be saying there? But
Well, Ignite is interesting. Actually, I'm not speaking at Ignite.
Okay.
I was going to, but I now am going to go to our labs in Copenhagen next week, whilst Ignite is going on, to actually meet with some of the physicists, because my next piece of work that I'm working on is actually a piece of hardware, a piece of software, cloud-based software, that should make their lives a little easier in order to get the qubit going. So, so that's kind of, we're all gunning for the first qubit in a very, very tangible, very, very, very straightforward, like this is literally what I do on a day job kind of thing.
That's exciting.
Yeah.
Very exciting.
Exactly.
That's great. John, thank you very much. It's beginning to soak in, I think, and for a lot of our listeners probably the same way, but thanks for being with us.
Thank you so much. I'm very, very privileged to be here.
You bet. And we'll see you next time on .NET Rocks.